trig. We like trig. Actually, we do. It's not as bad as you would think, especially when we have natural logs in our back pocket. The idea, though, with trig is to try and identify the u and du, which means you're looking for separate pieces. When you have just one term here, it's really two terms combined into a new function. Really, in all of trig, we just use sine and cosine, but we use it in different ways. So looking at tangent, I'm starting to think that's the same as sine of x over cosine of x. Now, I kind of have a setup here where I can do a u substitution. If u equals cosine of x, then the derivative of both sides gives me du equals negative sine of x dx. And that's almost exactly what I have. The only difference is I need the negative. In order to balance the negative, I'll put one on the inside and one on the outside. Negative times a negative is a positive. But now I can translate this into du and u, so it's a negative on the outside still. Then I have a du over u. Well, that's easy. That's just negative natural log absolute value of u plus c. So now I have negative natural log, and I can substitute the u back in. It happened to be cosine of x plus c. Problem 1, or number 9, pardon me, done. For this next one, it's similar. We just have a couple of layers, so we're going to have to be careful with the derivatives of u and du. When it says cotangent 3x, that's really cosine 3x over sine 3x, and of course the dx here. Of these two, start using your instincts. That bottom piece is going to be our u, since we're dealing with natural logs. U equals sine 3x. Then take the derivative of both sides. Du equals cosine 3x dx. But there's a chain rule in here. Since we have an inside function, it's cosine 3x times 3 times dx. Well, I have the cosine 3x. What I don't have is this 3. So I need to balance that. I need to put a 3 in here, but balance it with a 1/3 on the outside. In the end, that gives me 1/3 times the integral. I have 3 cosine 3x on top. That's the same as my du. On the bottom, I have sine x, and that's u. That's pretty easy, because this is just going to be 1/3 natural log of the absolute value of u plus c. That tells me that I have 1/3 natural log of the absolute value of sine 3x plus c. New color. When we do a u substitution, as we've done in the last couple, if it's not directly obvious which one to use, in general, you want to use the more complex one that has multiple layers. And if I look at these two parts of the fraction, I notice that the bottom one's a little more complex. So I'm going to go with that. That, to me, means that I have u equals 2 plus sine of x. Then du is just cosine of x dx. I actually don't have to do any balancing. I have all the pieces I need. Here's my du on top, and here's my u on bottom. So it's the integral of du over u, which is just equal to the natural log of the absolute value of u plus c. So now I substitute u back in. It's natural log of the absolute value of 2 plus sine x plus c. One more and we are done with this page. And then we only got one more page at all to cover. Alright, now when you look at this one, it's immediately starting to get a little bit sketchy, a little bit harder to do. Especially since I look at it and there's a lot of different algebra tricks we could do. Try try and figure it out. So let's try one. I'm not sure if this is going to work, but let's see what it does. If I have 1 over cosine squared of x times tangent x, well, this tangent x is really sine over cosine. Now, this isn't going to help me if I reduce these two pieces here. If I cancel this cosine x with one of the other cosine x's from that piece, it leaves me with the integral 1 over sine x cosine x. That does nothing for me. Well, let's go back and see if we can figure something else out. It's not directly obvious, but if I were to rewrite this in two separate terms, splitting right here, it would be the integral of 1 over cosine squared x times 1 over tangent x dx. Looking at those two pieces, it's not immediately obvious that they're related, but this first one does have a relationship that's a little more obvious if we rewrite it as secant squared x times 1 over tangent x. dx. Now that I'm looking at these pieces, I can even put them back together. Secant squared x over tangent x dx. Does anybody see it now? Hopefully you're beginning to see something about the relationship between these two pieces. If I say u equals tangent x, then du is equal to secant squared x dx. So I have my old pattern that I've been doing all day, du over u, which equals natural log of the absolute value of u plus c. So in this case, it's going to equal natural log of the absolute value of tangent of x plus c. One more and we are done. The difference between these and all the other ones, they're definite integrals. No more plus that constant of integration. Now we're going to evaluate the top minus the bottom. So let's do it. First one, let's start with blue. Using our u substitution from before, if I say that u equals 2x plus 1, then what's du? Well, it'd be 2 dx. If I look at this 4, that 4 is the same thing as 2 times 2. I need just one of those two, so I'm going to factor out the other two. So I'm still going to have 0 to 4. I have 2. I got 2 dx on top and 2x plus 1 on bottom. Now I have the derivative on top, the original on bottom. That means it's going to be 2 times the natural log of the absolute value of 2x plus 1. We're going to evaluate that from 0 to 4. So we're going to do the top minus the bottom. That means I'll have 2 times the natural log of, when I plug in the 4, it's going to be the absolute value of 2 times 4 plus 1 is 9. Minus 2 times the natural log of the absolute value of 2 times 0 plus 1 is 1. This conveniently helps us over here. The natural log of 1 is 0. So this whole term is 0. So it's just 2 times the natural log of 9. Now notice I don't need the absolute value because the absolute value of 9 is equal to 9. The second one, there's already a purple mark there. Let's go ahead and stick with that. This is another one of those that makes a little more sense when you kind of separate the fraction a little bit. So let's put 1 over x times 1 over natural log of x dx. And we're going from e to e squared. Well, if I'm looking at these pieces, I notice that the 1 over x is the derivative of natural log of x. So if I were to say u equals natural log of x, then du equals 1 over x dx. That means that I would have the integral of du over u up here, which we know from all the work we've been doing is natural log times the absolute value of u plus c if we had an indefinite integral, but this one's going to have boundaries. Let's go ahead and put it back in terms of x's so we can use these two boundaries here. So we'll have natural log of the absolute value of natural log of x we're going to evaluate that from e squared and e. So when I do my top minus bottom pieces, when I plug in e squared, it's going to be the natural log of e squared. Well, the natural log of e squared is really just 2. So it's going to wind up being the natural log of 2 for the top. I plug in my second boundary here. This should be e to the first power for the lower one. Let's erase that. For the second one, it's going to be natural log of the absolute value of natural log of e. Natural log of e is just 1, so it's the natural log of 1, which is already positive. So I have the natural log of 2 minus the natural log of 1. Natural log of 1 is 0. So my answer is really just natural log of 2. Last one, and then we are done. Sin x and 1 plus cosine x. Use some intuition. What have we been doing all day? What have we been using for our u in the substitution? The bottom tends to be our u. So I'm going to say u equals 1 plus cosine x. Then du, the derivative of 1 is 0. The derivative of cosine is negative sine x dx. So that means I need a negative here. Let's balance it with a negative on the outside. So I'm going to have a negative times the integral of du over u. Of course, we know that means negative natural log, absolute value of u plus c. Let's write it back in terms of x so we can put in our boundaries as well, because those are in terms of x. It means it's going to be a negative. We're going to evaluate this from 0 to pi over 2. And it's going to have the natural log of the absolute value of 1 plus cosine x. Well, if I were to plug in cosine x here, cosine of pi over 2 is 0. So the first top minus bottom, the first part, the top, is going to be negative natural log of 1 plus 0. The bottom is going to be negative natural log of cosine of 0 is 1. So it's going to be 1 plus 1. These two negatives make positive. So we have negative natural log of 1 plus 0, which is just 0, plus natural log of 2. Your answer is just natural log of 2. Again, that's crazy. Same answer twice in a row. We are done. Go back, watch again, review, practice, keep on learning.